To determine the maximum size dual element time delay fuse for protecting a 3-phase 40 horsepower motor at 460 volts, we need to refer to the National Electrical Code, specifically Article 430, which covers motors, motor circuits, and controllers. The first step is to find the full load current of the motor. According to Table 430.250 in the NEC, a 40 horsepower 3-phase motor operating at 460 volts has a full load current of 52 amps. Next, we need to determine the appropriate fuse size based on the motor's full load current. According to NEC section 430.52, the maximum rating or setting for a motor branch circuit, short circuit, and ground fault protective device, such as a fuse, depends on the type of motor and the type of protective device. For a dual element time delay fuse, the maximum rating is typically 175% of the motor's full load current. Now, let's calculate 175% of the full load current. 52 amps multiplied by 1.75 equals 91 amps. This means that the fuse should be rated at or below 91 amps according to the general rule. However, there is an exception. Exception number 2 in NEC section 430.52 allows for a higher fuse rating if the calculated value does not correspond to a standard fuse size. In this case, we are permitted to increase the fuse size to the next highest standard fuse size. Furthermore, if the motor controller is marked to permit overload protection selection at 225% of the full load current, you can use that value instead of 175%. In this scenario, 52 amps multiplied by 2.25 equals 117 amps. Now, we need to consider section 240.6, which lists the standard ampere ratings for fuses and inverse time circuit breakers. The standard fuse sizes near 91 amps are 90 amps and 100 amps. The standard fuse sizes near 117 amps are 110 amps, 125 amps, and 150 amps. Given that the question asks for the maximum size fuse, and assuming the motor does not have adjustable trip settings, we initially calculated 91 amps. We would then select the next standard size up, which is 100 amps. However, if the motor has provisions for externally adjustable overload trip settings, as mentioned in exception number 2 for 430.52, we can use 225% of the full load current, which equals 117 amps. In this case, we can then go to the next standard size fuse according to 240.6. This would allow us to use a 125 amp fuse. Therefore, the correct answer, considering the allowance for upsizing per the exception, is 125 amps. Now, let's discuss what to do if the motor fails to start with a 100 amp fuse. If the motor fails to start with a 100 amp fuse, it does not automatically mean that a larger fuse is required. There could be several reasons why the motor is not starting. Firstly, it's crucial to ensure that the motor itself is in good working condition. Check for any signs of damage, such as burnt windings or a seized rotor. Use an ohmmeter to test the motor windings for continuity and insulation resistance. Compare the readings to the manufacturer's specifications. If the motor is faulty, replacing it may be necessary. Secondly, inspect all electrical connections in the motor circuit. Loose or corroded connections can cause voltage drops and prevent the motor from starting. Ensure that all connections are clean and tight. Use a torque wrench to tighten connections to the specified torque. Thirdly, verify that the supply voltage to the motor is within the acceptable range. Use a voltmeter to measure the voltage at the motor terminals while the motor is attempting to start. If the voltage is too low, investigate the cause of the voltage drop. This could be due to undersized conductors, a weak power source, or excessive loading on the circuit. Fourthly, check the motor overload protection. The motor overload protection device is designed to protect the motor from overheating due to excessive current. If the overload protection device is tripped, it will need to be reset before the motor can start. Determine the cause of the overload before resetting the device. Fifthly, examine the motor starter. The motor starter is responsible for starting and stopping the motor. If the motor starter is faulty, it may not be able to provide the necessary current to start the motor. Check the contacts and coils of the motor starter for signs of damage. Use a multimeter to test the operation of the motor starter. Sixthly, look into any mechanical issues. Make sure the motor is not mechanically overloaded. Disconnect the motor from the load and try to start it. If the motor starts without the load, there may be a problem with the driven equipment. Check for excessive friction, binding, or other mechanical issues. If, after troubleshooting all these potential issues, the motor still fails to start with a 100 amp fuse, then it may be necessary to consider using a larger fuse up to the maximum allowed by the NEC, which in this case is 125 amps, given the provisions for adjustable trip settings. However, it is important to carefully consider the potential consequences of using a larger fuse. A larger fuse will provide less protection for the motor in the event of a short circuit or ground fault. Therefore, it is essential to ensure that the motor is properly protected by other means such as overload relays. In summary, to determine the appropriate fuse size for a 40 horsepower motor, first find the full load current from table 430.250, then apply the multipliers from 430.52, considering any exceptions that may apply, such as exception number 2, and finally refer to 240.6 for standard fuse sizes. If the motor fails to start, troubleshoot potential issues before increasing the fuse size, and always prioritize motor protection. Remember that electrical work can be dangerous. Always follow safe work practices and consult with a qualified electrician if you are not comfortable performing the work yourself. It's important to emphasize the significance of using dual-element time delay fuses for motor protection. These fuses are specifically designed to handle the high inrush currents that occur when a motor starts, while still providing protection against overloads and short circuits. Standard fuses may blow unnecessarily due to the inrush current, while time delay fuses can tolerate this current for a short period of time, allowing the motor to start without interrupting the circuit. Choosing the correct type of fuse is essential for ensuring both motor protection and reliable operation. Additionally, it's worth noting that the NEC provides specific guidelines for the installation and wiring of motor circuits. These guidelines cover topics such as conductor sizing, overcurrent protection, and grounding. It's crucial to follow these guidelines to ensure the safety and reliability of the electrical system. Failure to comply with the NEC can result in electrical hazards, equipment damage, and even legal penalties. Always refer to the latest edition of the NEC for the most up-to-date information and requirements. Furthermore, it is recommended to consult with a qualified electrical engineer or inspector to ensure that the motor circuit is properly designed and installed. They can provide expert advice and guidance on selecting the appropriate components, complying with the NEC, and ensuring the safety of the electrical system. Proper motor protection is essential for preventing costly downtime and equipment damage. By following the guidelines in the NEC and consulting with qualified professionals, you can ensure that your motors are properly protected and operate reliably for years to come. Now let's delve deeper into the concept of full load current and its importance in motor protection. Full load current, often abbreviated as FLC, is the amount of current that a motor draws when it is operating at its rated horsepower and voltage. It is a critical parameter for determining the appropriate size of conductors, overcurrent protection devices, and motor starters. The full load current of a motor is typically listed on the motor's nameplate. This information is essential for selecting the correct components for the motor circuit. As we discussed earlier, Table 430.250 in the NEC provides full load current values for various types of motors based on their horsepower and voltage ratings. This table is a valuable resource for electricians and engineers when designing motor circuits. It's important to note that the full load current is not the same as the starting current. The starting current of a motor can be several times higher than the full load current. This is due to the fact that the motor needs to overcome inertia and accelerate the load from a standstill. The high starting current can cause voltage drops and may require the use of special starting methods, such as reduced voltage starters, to limit the inrush current. Overcurrent protection devices, such as fuses and circuit breakers, must be sized to accommodate the motor's starting current while still providing protection against overloads and short circuits. This is why time delay fuses are often used for motor protection, as they can tolerate the high starting current without tripping unnecessarily. In addition to overcurrent protection, motors also require overload protection. Overload protection is designed to protect the motor from overheating due to excessive current draw. Overloads can be caused by a variety of factors, such as a mechanical overload, a voltage imbalance, or a winding fault. Overload relays are commonly used to provide overload protection for motors. These relays are designed to trip when the motor current exceeds a predetermined value for a specified period of time. When the overload relay trips, it interrupts the motor circuit and prevents the motor from overheating. It is important to select an overload relay that is properly sized for the motor's full load current. The overload relay should be set to trip at a current value that is slightly higher than the motor's full load current, but below the motor's maximum allowable current. Proper overload protection is essential for extending the life of the motor and preventing costly repairs. In conclusion, understanding the concepts of full load current, overcurrent protection, and overload protection is crucial for ensuring the safety and reliability of motor circuits. By following the guidelines in the NEC and consulting with qualified professionals, you can properly protect your motors and prevent costly downtime and equipment damage. And always ensure to use the correct and latest version of the NEC.